What lies in the places our telescopes rarely visit? Beyond the bright stars are shadows we've never explored. What secrets sleep in the quietest corners of our galaxy? Not every part of the Milky Way shines. Some parts whisper. What did the universe leave behind? In the corners, we forgot to look. Let's go where light fades and mystery begins, into the forgotten corners of the Milky Way. Have you ever stood beneath a clear night sky, watching that magnificent river of stars we call the Milky Way stretch across the heavens? It seems so vast, so complete. But what if I told you that what you see is not alone? Our galaxy, this spiral of hundreds of billions of stars that we call home, has companions. Dozens of smaller galaxies surround the Milky Way, quiet, dim, and often ignored by all but the most dedicated skywatchers. These are the forgotten galaxies, shadows from the early cosmos still faithfully circling us after billions of years. Some are visible to the naked eye from the southern hemisphere, like gentle smudges against the black canvas of night. Others are so faint that even the most powerful telescopes struggle to find them until recent years. Yet, each carries stories from the beginning of our universe. They drift through the darkness around us, gravitationally bound to our galaxy, pulled into slow, ancient orbits. Some will eventually merge with the Milky Way, their stars becoming part of our galactic family. Others will continue their silent journeys for billions of years to come. Close your eyes and imagine the space around our galaxy, not empty, but filled with these celestial companions. Imagine them moving in slow, deliberate paths, their stars burning with light almost too faint to detect. Some have been orbiting for almost as long as the universe has existed. Others were once independent, but have been captured by our galaxy's immense gravitational pull. The light from these forgotten galaxies has traveled incredible distances to reach us. Some of their stars were born before the Earth formed. Their patterns and compositions tell us about the earliest days of the cosmos, when the first structures began to take shape in the aftermath of the Big Bang. In the quiet of night, while most of humanity sleeps, these galaxies continue their silent orbits. The large and small Magellanic Clouds hover above the southern horizon, visible as misty patches against the dark. Dozens more circle unseen, their faint glow lost in the vastness of space, or hidden behind the bright band of the Milky Way. Scientists estimate that there may be hundreds of these satellite galaxies surrounding us, most still undiscovered. Each time we develop more sensitive instruments, we find more of these cosmic neighbors. They hide in plain sight, overshadowed by the brilliance of our own galaxy, but carrying equally important chapters of the universal story. These forgotten galaxies hold secrets about dark matter, that mysterious substance that makes up most of the mass in our universe but cannot be directly observed. They show us how galaxies evolve over cosmic time, merging and transforming through gravitational interactions. They preserve conditions from the early universe that have long since changed in larger galaxies. Think of them as time capsules, preserving the chemistry and stellar populations of the early universe. While our Milky Way has transformed itself many times over through collisions and star formation, many of these satellite galaxies have remained largely unchanged for billions of years. They are cosmic fossils, their light a direct window into the ancient past. As you look at the night sky, consider that between the stars you can see are entire galaxies you cannot. Consider that the space around our Milky Way is not empty, but filled with these silent watchers. Some are being slowly torn apart by our galaxy's gravitational pull, their stars forming long streams that wrap around us like cosmic ribbons. Others maintain their compact forms, resisting disruption for now. The relationship between these satellite galaxies and our Milky Way is complex. They affect each other through gravity, exchanging energy, and sometimes material. Gas from these smaller galaxies can fall into the Milky Way, fueling new star formation, Stars from our galaxy can be pulled outward by their passing. The dance is slow but constant, measured in millions and billions of years. What would it be like to stand on a planet in one of these forgotten galaxies? To look up at a night sky dominated by the enormous spiral of the Milky Way. From there, our galaxy would appear as a vast, bright structure filling much of the sky, its spiral arms clearly visible, its central bulge glowing with the light of billions of stars. Tonight, we journey beyond the bright spiral arms of our galaxy to discover what hides just beyond. We seek out these overlooked companions that have witnessed the entire history of our cosmos. In their dim light and ancient stars, we find clues to how galaxies form, how dark matter shapes our universe. The night sky above you holds more than stars. It holds entire island universes, each with billions of stars of their own, orbiting our cosmic home in a dance that has continued for billions of years. As you drift towards sleep, imagine these forgotten galaxies continuing their eternal orbits, timeless witnesses to cosmic history. The Milky Way shines across our sky, but just beyond its light are shadows, tiny galaxies that orbit quietly, ghosts of ancient structure, reminders of how the cosmos once built itself. They are many, and they are still here. Tonight, we remember the forgotten galaxies of the Milky Way. What happens when galaxies meet in the vastness of space? When massive collections of stars, gas, and dust come close enough to feel each other's gravitational influence? The answer lies in the concept of satellite galaxies, the celestial companions that orbit larger galaxies throughout the universe. Satellite galaxies are smaller galaxies that are gravitationally bound to a larger host galaxy. Think of them as cosmic moons, except instead of orbiting a planet, they orbit an entire galaxy. These satellites range dramatically in size and brightness, from those containing billions of stars to tiny collections with just a few 100,000. What unites them is their relationship with their host, trapped in orbits that may take billions of years to complete. The Milky Way is not alone in having these companions. Nearly all large galaxies have their own entourage of smaller satellite galaxies. In fact, astronomers organize galaxies into groups and clusters based on these gravitational relationships. Our Milky Way belongs to what we call the local group, a collection of more than 50 galaxies bound together by gravity, spanning a region about 10 million light-years across. Within this local group, there are two dominant galaxies, our Milky Way and the Andromeda Galaxy, each with their own system of satellite galaxies. These two giants contain most of the mass in our local group, with their satellites arranged around them like cosmic courtiers around galactic royalty. The space between these major galaxies isn't empty, but filled with smaller galaxies feeling the gravitational pull of both giants. Let's focus on our own galactic neighborhood. The Milky Way has at least 50 confirmed satellite galaxies, though astronomers believe there may be hundreds more still undiscovered. The most famous and visible of these companions are the Large and Small Magellanic Clouds, visible to the naked eye in the southern hemisphere as fuzzy patches in the night sky. But beyond these bright companions are dozens of dimmer galaxies, with names like Sagittarius Dwarf Spheroidal, Ursa Minor Dwarf, and Draco Dwarf. These names point to an important characteristic of most satellite galaxies. The term dwarf appears frequently because compared to spiral galaxies like our own, they are indeed diminutive. Most satellite galaxies around the Milky Way are classified as dwarf spheroidal galaxies, meaning they are relatively small and have a roughly spherical shape, with no clear structure like the beautiful spiral arms of the Milky Way. Imagine looking up at the night sky from a planet in one of these dwarf spheroidal galaxies. You would see fewer stars in your immediate sky, as these galaxies contain far fewer stars than the Milky Way. But dominating your view would be the magnificent spiral of our galaxy, appearing many times larger than the full moon does from Earth, its bright arms and central bulge, clearly visible even to the naked eye. What makes these satellite galaxies particularly fascinating is their incredible diversity. Some, like the Sagittarius dwarf spheroidal galaxy, orbit very close to the Milky Way and are currently being torn apart by our galaxy's tremendous gravitational forces. Others, like the Leo I dwarf galaxy, maintain a distance of several 100,000 light-years, completing one orbit around the Milky Way in billions of years. Some of these satellites, like the Magellanic Clouds, are irregular in shape and actively forming new stars. Their blue stellar populations indicate recent star formation, showing they still have enough gas to birth new suns. Others, like many of the dwarf spheroidals, are composed almost entirely of ancient stars, with no new star formation having occurred for billions of years. They appear redder, their stars old and cool. The orbits of these satellite galaxies tell us fascinating stories about their histories. Some appear to orbit in a relatively flat plane around the Milky Way, suggesting they may have formed together or been captured as a group. Others follow more random paths, possibly indicating they were captured individually through chance encounters in the vastness of space. What's particularly striking about these satellite galaxies is how long they've been circling our Milky Way. Many have completed dozens of orbits around our galaxy, each orbit taking hundreds of millions or even billions of years. They have been our silent companions since the early days of the universe, their positions slowly shifting across eons as they continue their cosmic journeys. These satellite galaxies aren't merely passive observers of the Milky Way. They interact with our galaxy in profound ways. The Sagittarius dwarf galaxy, for instance, has passed through the disk of the Milky Way multiple times in its history. Each passage creates ripples in our galaxy's structure, like stones dropped in a cosmic pond. The stars in our galaxy's disk still show the effects of these passages, with waves of stellar motion that astronomers can detect and measure. Many of our satellite galaxies appear to be losing mass to the Milky Way, their outer stars being pulled away by tidal forces to form long streams that wrap around our galaxy like ethereal rivers of stars. The most dramatic example is the Sagittarius Stream, a vast arc of stars wrapping completely around the Milky Way, the remnants of the Sagittarius dwarf galaxy being slowly incorporated into our own. Perhaps the most mysterious and important aspect of satellite galaxies is what they tell us about dark matter. When astronomers measure the motion of stars in these dwarf galaxies, they find something remarkable. The stars move much faster than can be explained by the visible mass alone. This indicates these small galaxies are dominated by dark matter, the invisible substance that makes up most of the mass in our universe. In fact, some of the ultra-faint dwarf galaxies orbiting the Milky Way appear to be among the most dark matter-dominated objects known. For every visible star, there may be thousands of times more mass in the form of dark matter. These galaxies are essentially dark matter halos, with just a sprinkling of visible stars, making them ideal laboratories for studying this mysterious substance. The relationship between satellite galaxies and their hosts appears to be universal. When we look at other large galaxies, from Andromeda to more distant systems, we find similar arrangements of smaller galaxies orbiting larger ones. This hierarchical structure seems to be fundamental to how galaxies organize themselves across the cosmos. In recent decades, our understanding of the Milky Way's satellite system has expanded dramatically. Before the year 2000, we knew of only 9 satellite galaxies around the Milky Way. Today, that number exceeds 50 and continues to grow as more sensitive surveys scan the sky. Each newly discovered satellite adds another piece to the puzzle of how our galactic neighborhood formed and evolved. Every satellite galaxy orbiting the Milky Way has its own unique story, its own journey through time and space. Together, they form a cosmic community bound by gravity and shared history. They remind us that even in the seeming emptiness of space, relationships form between the greatest structures in our universe. Cosmic kinship extends beyond the boundaries of individual galaxies, creating families of stellar systems moving together through the cosmos. As the night deepens and your thoughts drift towards sleep, remember that above you, Beyond the visible stars of the Milky Way, dozens of forgotten galaxies continue their ancient orbits. Though they may seem insignificant compared to the brilliance of our own galaxy, they are silent keepers of cosmic history, their faint light carrying messages from the beginning of time. If you've ever gazed at the night sky from the southern hemisphere, you may have noticed two unusual cloudy patches amidst the stars. Too large to be stars, too fuzzy to be planets, these misty celestial objects have captivated human observers for thousands of years. Indigenous Australians saw them as campfires in the sky. Polynesian navigators used them to guide their voyages across vast oceans. To early European explorers, they became known as the Magellanic Clouds, named after Ferdinand Magellan, whose crew documented them during their historic circumnavigation of the globe in the early 16th century. What are these mysterious clouds in our southern sky? They are our closest galactic neighbors, the large and small Magellanic Clouds. Unlike the more distant and fainter satellite galaxies that orbit the Milky Way unseen by the naked eye, these two companions announce their presence boldly, visible even without telescopes. At distances of roughly 160,000 and 200,000 light-years respectively, the large and small Magellanic Clouds are close enough that we can study them in remarkable detail. The large Magellanic Cloud spans about 14,000 light-years across, making it roughly 1/10 the size of our Milky Way. Though smaller than our galaxy, it still contains approximately 30 billion stars, a truly enormous collection of suns. The small Magellanic Cloud is more modest, spanning about 7,000 light-years and containing several billion stars. Together, they form the most massive and luminous members of the Milky Way's satellite family. What makes these galaxies particularly fascinating is their appearance. Unlike the elegant spiral of the Milky Way or the featureless spheroids of many dwarf galaxies, the Magellanic Clouds are irregular galaxies with no defined structure. They appear as chaotic collections of stars, gas, and dust, their shapes distorted by gravitational interactions with the Milky Way and with each other. This irregularity tells us something important about these galaxies. They are dynamic, active systems undergoing dramatic changes. Within the large Magellanic Cloud, we find regions of intense star formation, where new stars are being born from collapsing clouds of gas and dust. The most famous of these stellar nurseries is the Tarantula Nebula, a vast complex of gas and newly formed stars that would be visible from Earth at the distance of the Moon if it were that close. The Tarantula Nebula alone outshines many entire galaxies. It represents one of the most active star-forming regions in our local group of galaxies. Within its glowing clouds, astronomers have identified thousands of young, massive stars, some more than 100 times the mass of our Sun. These stellar giants burn hot and bright, but live short lives, exploding as supernovae after just a few million years. Indeed, in 1987, astronomers witnessed a spectacular supernova in the Large Magellanic Cloud, the closest observed supernova to Earth since the invention of the telescope. This explosion, designated SN 1987A, provided unprecedented insights into the death of massive stars and continues to be studied today as its shock waves expand through the surrounding space. The small Magellanic Cloud also contains regions of star formation. Though less dramatically than its larger companion, it has a lower content of heavy elements, suggesting it has experienced less processing of its original gas through generations of stars. In many ways, the small Magellanic Cloud resembles galaxies from the early universe, making it a valuable laboratory for studying how stars form in environments similar to those that existed billions of years ago. What makes the Magellanic Clouds even more intriguing is the evidence of their interaction with each other and with the Milky Way. Between these two galaxies stretches a bridge of gas, appropriately named the Magellanic Bridge. This tenuous connection contains not only hydrogen gas, but also young stars that appear to have formed within the bridge itself, born from gas pulled out of the two galaxies by their mutual gravitational attraction. Even more spectacular is the Magellanic Stream, an enormous trail of gas extending from the Magellanic Clouds in a great arc that wraps more than halfway around the Milky Way. Spanning more than 100 degrees across the sky, this stream contains enough hydrogen gas to create millions of stars the size of our Sun. It represents material being stripped from the Magellanic Clouds as they move through the halo of the Milky Way, like cosmic breadcrumbs marking their passage through space. The discovery of the Magellanic Stream in the 1970s revealed something profound about the relationship between the Magellanic Clouds and our galaxy. It showed that these interactions are not gentle or passive, but involve the transfer of enormous amounts of material. The Milky Way is slowly consuming gas from its brightest satellites, material that may eventually form new stars within our own galaxy. For many years, astronomers believed the Magellanic Clouds had been orbiting the Milky Way for billions of years, completing many circuits around our galaxy. However, more recent measurements of their motion have suggested a different story. The clouds appear to be moving faster than previously thought, possibly on their first close approach to the Milky Way. They may be relatively recent additions to our galaxy's family of satellites, captured by the Milky Way's gravity only within the last few billion years. What does the future hold for these bright companions? Computer simulations suggest that the Magellanic Clouds are on trajectories that will eventually bring them into closer encounters with the Milky Way. The Large Magellanic Cloud may collide with our galaxy in approximately 2.4 billion years, an event that will dramatically reshape both galaxies. The smaller cloud may follow, or it may be ejected into intergalactic space by the gravitational disruption of this cosmic collision. When we observe the Magellanic Clouds, we are seeing galaxies in transition. Once they may have been independent spiral galaxies, but their encounters with each other and with the Milky Way have distorted their structures into the irregular forms we see today. They are cosmic travelers whose journeys have brought them into the gravitational influence of our galaxy, their futures now tied to the Milky Ways. The light from the Magellanic Clouds takes more than 150,000 years to reach us. When the photons now reaching our telescopes began their journey, humans had not yet developed agriculture, written language, or built permanent settlements. Yet those ancient photons carry information about galaxies that, in cosmic terms, are our next-door neighbors. Studying the Magellanic Clouds gives us insights not only into these specific galaxies, but into fundamental processes that shape galaxies throughout the universe. They show us how galaxies interact and evolve, how stars form in different environments, and how gas moves between galaxies. Their proximity makes them ideal laboratories for testing our understanding of astrophysics. As you picture these bright neighbors in your mind, imagine the vast streams of gas flowing between them and our galaxy. Imagine the brilliant star-forming regions where new suns are being born, even as others die in spectacular explosions. Imagine the slow dance of three galaxies moving through space, their futures intertwined by gravity and chance. The Magellanic Clouds remind us that even the greatest structures in our universe are not isolated or unchanging. Galaxies move, interact, and transform each other over vast spans of time. They exchange material, influence each other's star formation, and sometimes merge completely. The bright smudges in our southern sky are not merely static objects, but dynamic systems with rich histories and dramatic futures. Tonight, as the sky darkens and the stars appear, remember that among those points of light lie two small galaxies, visible to the naked eye, yet containing billions of stars. In their faint glow lies evidence of cosmic processes that have shaped our universe since its earliest days. They are not just our brightest neighbors, but windows into the fundamental nature of galaxies throughout the cosmos. What does it mean to be nearly invisible in a universe full of light? Among the satellite galaxies orbiting our Milky Way, there exists a population so dim, so ethereal, that they remained completely unknown until the 21st century. These are the ultra-faint dwarf galaxies, cosmic ghosts that challenge our very definition of what a galaxy is. Their discovery has revolutionized our understanding of the galactic neighborhood and opened new windows into the early universe. Imagine looking at a clear night sky through a powerful telescope. You see countless stars, perhaps a few distant galaxies. But hidden among those stars, almost impossible to distinguish, are entire galaxies containing thousands of stars. So faint are these systems that they emit less light than a single bright star in the Milky Way. Their surface brightness is so low that the light from the night sky itself can easily overwhelm them. They are, in a very real sense, galaxies hiding in plain sight. The story of these elusive galaxies begins in 2005, when astronomers analyzing data from the Sloan Digital Sky Survey made a remarkable discovery. By carefully filtering the survey data to look for subtle overdensities of stars with similar properties, they found something unexpected. A tiny, incredibly faint collection of stars approximately 280,000 light-years from Earth in the constellation Ursa Major. Named Willman 1 after its discoverer, this object contained only about 1,000 stars, yet showed evidence of being a distinct galaxy rather than a star cluster. This discovery was soon followed by others. Within a few years, astronomers had identified over a dozen of these ultra-faint dwarf galaxies orbiting the Milky Way. Objects with names like Segway 1, Boots 1, Reticulum 2, and Draco 2 joined the catalogue of known satellite galaxies. Each contained between a few hundred and a few thousand stars, making them hundreds or thousands of times less massive than previously known dwarf galaxies. What makes these objects particularly fascinating is the question they raise: what exactly is a galaxy? Traditionally, astronomers defined galaxies as massive collections of stars, gas, and dust bound together by gravity, typically containing billions of stars. But these ultra-faint dwarfs contain fewer stars than many globular clusters, which are not considered galaxies but rather tightly bound collections of stars within a galaxy. The key distinction lies not in the number of stars, but in the presence of dark matter. When astronomers measure the motions of stars in these ultra-faint dwarfs, they find something remarkable. The stars move much faster than can be explained by the gravitational pull of the visible matter alone. This indicates the presence of a substantial amount of dark matter, the invisible substance that makes up most of the mass in our universe. In fact, these ultra-faint dwarfs appear to be among the most dark matter-dominated objects known in the universe. For every visible star, there may be thousands or even tens of thousands of times more mass in the form of dark matter. They are essentially dark matter halos with just a sprinkling of visible stars, like a few grains of sand scattered across a vast, invisible beach. This extreme dark matter content is a key reason astronomers classify them as galaxies rather than star clusters. Globular clusters, by contrast, contain no significant amount of dark matter. The ultra-faint dwarfs are not simply small collections of stars, but fundamental cosmic structures shaped by the same processes that formed all galaxies, including our Milky Way. What makes these galaxies even more remarkable is their age. When astronomers analyze the chemical composition of stars in ultra-faint dwarfs, they find them to be extremely poor in elements heavier than hydrogen and helium. This indicates that they formed very early in the history of the universe, before multiple generations of stars had enriched the cosmic environment with heavier elements. Indeed, some of these galaxies appear to contain stars that formed less than 1 billion years after the Big Bang, making them among the oldest stellar systems known. They are time capsules from the dawn of galaxy formation, preserving conditions that existed when the universe was just beginning to form its first structures. Their very existence poses challenges to our models of galaxy formation. Traditional theories suggested that galaxies need a certain minimum mass to form and retain stars. Below this threshold, it was thought that processes like supernova explosions would expel all gas from the small galaxy, preventing star formation. Yet these ultra-faint dwarfs managed to form and retain at least some stars despite their minimal mass. The Segway 1 dwarf galaxy, discovered in 2006, illustrates the extreme nature of these objects. At about 75,000 light-years from Earth, This galaxy contains only a few hundred stars visible to our telescopes. Its total luminosity is about 300 times fainter than the average globular cluster, making it less luminous than a single bright giant star. Yet its stars move at speeds indicating a total mass thousands of times greater than can be accounted for by the visible stars alone. Similarly, the Reticulum II dwarf galaxy, discovered in 2015, contains only a few thousand stars, but shows evidence of complex chemical enrichment processes. Some of its stars contain unusually high amounts of heavy elements like gold and silver, suggesting that this tiny galaxy witnessed a neutron-star merger, one of the most energetic events in the universe, and a key source of these heavy elements. What is perhaps most fascinating about these ultra-faint dwarfs is how many more likely remain undiscovered. The ones we have found are mostly relatively close to the Milky Way and in parts of the sky that have been surveyed with sensitive instruments. Large regions of the sky remain unsearched, and many ultra-faint dwarfs may be too distant or too obscured by the disk of the Milky Way to be easily detected. Astronomers estimate that there could be hundreds of these galaxies orbiting the Milky Way, most still waiting to be discovered. Each new survey with more sensitive instruments reveals more of these faint companions. The Vera Rubin Observatory, scheduled to begin operations in the mid-2020s, is expected to discover dozens more ultra-faint dwarf galaxies, dramatically expanding our census of the Milky Way's satellites. Why does this matter? These galaxies, despite their diminutive size and faintness, play crucial roles in our understanding of the universe. They help resolve what cosmologists call the missing satellites problem, a discrepancy between the number of satellite galaxies predicted by dark matter models and the number actually observed. The discovery of numerous ultra-faint dwarfs has helped bring observation closer to theoretical prediction. They also provide unique laboratories for studying star formation in extreme environments, for testing theories of how the first galaxies formed, and for probing the nature of dark matter itself. Some theories of dark matter predict that it should produce detectable gamma-ray signals when dark matter particles interact. The high dark matter concentration in ultra-faint dwarfs makes them ideal targets for searching for such signals. Imagine the journey of an ultra-faint dwarf galaxy through cosmic time. It forms in the early universe, a small concentration of dark matter that manages to gather enough gas to form a few thousand stars. For billions of years, it exists as an independent entity, slowly orbiting the growing Milky Way. Perhaps it loses gas to the larger galaxy, preventing further star formation. Its stars age, the brightest ones exploding as supernovae or expanding into red giants. Eventually, only the smallest, longest-lived stars remain, growing progressively redder and fainter. By the time humans evolve on Earth and develop the technology to detect these galaxies, they have been orbiting the Milky Way for most of cosmic history. They have completed dozens or hundreds of orbits, each taking hundreds of millions of years. They have witnessed the entire history of our galaxy, silent observers of cosmic evolution. Yet despite their ancient nature, these galaxies continue to evolve and change. Many are being slowly torn apart by the tidal forces of the Milky Way. Their stars are being stripped away, forming long streams that wrap around our galaxy. In billions of years, many will be completely disrupted, their stars becoming part of the Milky Way's halo, their distinct identities lost to time. As you close your eyes and imagine the night sky, remember that between the stars you can see are entire galaxies you cannot. Galaxies so faint that they eluded discovery until recently, yet so fundamental to our understanding of the universe. In their dim light and ancient stars, they tell stories of cosmic beginnings, of the first structures to form in our universe, of the mysterious dark matter that shapes cosmic evolution. The ultra-faint dwarfs remind us that the universe holds wonders still waiting to be discovered, that even in cosmic realms we think we understand, surprises lurk in the darkness. They teach us humility in the face of the vastness and complexity of our universe. And they show us that sometimes The most insignificant seeming objects can hold the most profound secrets. Have you ever wondered how scientists piece together the history of our universe? How do we know what happened billions of years ago, long before any human existed to observe cosmic events? The answer lies partly in the small, often overlooked satellite galaxies orbiting our Milky Way. These galactic companions serve as cosmic time capsules, preserving conditions from the early universe that have long since changed in larger galaxies like our own. Unlike the Milky Way, which has undergone continuous transformation throughout its lifetime, many satellite galaxies have remained relatively unchanged for billions of years. They are cosmic fossils, their stars and structure preserving information about the universe as it existed in its youth. By studying these galactic relics, astronomers can peer back in time, observing conditions that would otherwise be lost to us. Consider the chemical composition of stars in these satellite galaxies. When we analyze the light from stars in ultra-faint dwarf galaxies, we find them to be extraordinarily poor in elements heavier than hydrogen and helium. Astronomers refer to these elements collectively as metals, and their scarcity in these ancient galaxies tells us something profound about cosmic evolution. In the early universe, shortly after the Big Bang, only the lightest elements existed: hydrogen, helium, and trace amounts of lithium. All heavier elements were created later, forged in the nuclear furnaces of stars, and scattered through space when those stars died in supernova explosions. This process of cosmic enrichment has been ongoing for billions of years, gradually increasing the abundance of heavy elements throughout the universe. The stars in many satellite galaxies show chemical signatures indicating they formed before this enrichment process had progressed very far. Some contain stars that may have formed from gas that experienced only a single previous generation of star formation. These are among the most chemically primitive stars known, providing direct information about conditions in the early universe. By studying the detailed chemical composition of these stars, astronomers can reconstruct the history of element formation in the universe. They can determine which elements formed first, how quickly the cosmic environment became enriched with different elements, and how this process varied between different types of galaxies. This information is crucial for understanding the chemical evolution of our universe. Beyond their chemical composition, the satellite galaxies help us understand the process of galaxy formation itself. According to current theories, galaxies form hierarchically, with smaller structures forming first, and then merging to create larger ones. The satellite galaxies around the Milky Way represent structures that formed early, but never merged into larger systems, allowing us to study the building blocks of galaxy formation directly. The distribution and orbits of satellite galaxies also provide clues about how the Milky Way formed and evolved. By tracking the positions and movements of these galaxies, astronomers can reconstruct the assembly history of our galactic neighborhood. They can identify groups of satellites that may have entered the Milky Way's influence together, tracing back patterns of cosmic structure formation. Perhaps the most significant contribution these satellite galaxies make to our understanding of the universe involves dark matter, the mysterious substance that makes up about 85% of all matter in the cosmos. Dark matter doesn't interact with light or other forms of electromagnetic radiation, making it impossible to observe directly. Yet its gravitational influence shapes the formation and evolution of all cosmic structures. The satellite galaxies of the Milky Way, particularly the ultra-faint dwarfs, are among the most dark matter-dominated objects known. By measuring the motions of stars within these galaxies, astronomers can map the distribution of dark matter and test different theories about its nature. Do dark matter particles interact with each other? Does dark matter form a smooth distribution or clump together? The satellite galaxies offer some of our best opportunities to answer these questions. One particularly intriguing aspect of the Milky Way's satellite system is what astronomers call the missing satellites problem. Computer simulations based on dark matter theories predict that a galaxy the size of the Milky Way should have hundreds or even thousands of satellite galaxies. Until recently, however, we had observed only a few dozen. This discrepancy posed a significant challenge to our understanding of dark matter and galaxy formation. The discovery of numerous ultra-faint dwarf galaxies in recent years has partially resolved this tension, but differences between observation and theory remain. These differences provide valuable constraints on dark matter properties and on the processes that govern galaxy formation. By carefully cataloging and studying the satellite galaxies we can observe, astronomers refine their theories about those we cannot. The satellite galaxies also help us understand how larger galaxies grow over time. According to current models, much of the Milky Way's halo, the extended region of stars surrounding the visible disk, formed through the accretion of smaller galaxies. These galaxies were torn apart by the Milky Way's gravitational forces, their stars dispersing into the halo while largely maintaining their original orbits. By studying the current population of satellite galaxies, particularly those in the process of being disrupted, astronomers can observe this accretion process in action. They can see how tidal forces strip stars from these smaller galaxies, forming streams that eventually dissolve into the general halo population. This provides direct observational evidence for a key aspect of galaxy evolution. The Sagittarius dwarf galaxy, discovered in 1994, offers a dramatic example of this process. This satellite galaxy is currently passing through the disk of the Milky Way and is being torn apart by tidal forces. Its stars form a massive stream that wraps completely around our galaxy at least once. By mapping this stream and modeling the forces involved, astronomers can reconstruct the orbital history of the Sagittarius dwarf and gain insights into the mass distribution of the Milky Way itself. Similarly, the stellar streams associated with other disrupting satellites provide three-dimensional probes of the Milky Way's gravitational field. These streams are sensitive to the shape of the dark matter halo surrounding our galaxy, allowing astronomers to determine whether this halo is spherical, flattened, or triaxial in shape. This information is crucial for understanding the overall structure and evolution of the Milky Way. The satellite galaxies also serve as laboratories for studying star formation under different conditions. In the smallest ultra-faint dwarfs, star formation appears to have been brief and inefficient, producing relatively few stars before stopping completely. In contrast, the Magellanic Clouds show ongoing star formation billions of years after their formation. By comparing these different histories, astronomers can identify the factors that control the star formation process in galaxies of different sizes. One particularly intriguing question involves what astronomers call reionization, a period early in cosmic history when the first stars and galaxies produced enough ultraviolet radiation to ionize hydrogen throughout the universe. This event had profound effects on subsequent galaxy formation, particularly for the smallest galaxies. By studying the star formation histories of different satellite galaxies, astronomers can determine how they were affected by reionization and constrain when this event occurred. The satellite galaxies even help us test the fundamental laws of physics. Some alternative theories of gravity, proposed as explanations for cosmic phenomena without invoking dark matter, make specific predictions about the dynamics of small galaxies. By measuring the motions of stars in satellite galaxies with increasing precision, astronomers can test these alternative theories against the standard dark matter paradigm. Looking toward the future, our understanding of the Milky Way's satellite system will continue to deepen as new observational facilities come online. The Vera Rubin Observatory, with its planned legacy survey of space and time, will scan the entire visible sky repeatedly over a decade, likely discovering many more faint satellite galaxies. The Nancy Grace Roman Space Telescope and the Euclid mission will provide unprecedented views of the stellar populations in known satellite. As you drift toward sleep, consider the profound interconnectedness of cosmic structures. The smallest galaxies help us understand the largest scales of the universe. The oldest stellar systems inform our knowledge of cosmic evolution. The faintest objects illuminate the nature of the invisible dark matter that dominates the cosmos. In astronomy, as in many fields of human inquiry, The overlooked and seemingly insignificant often hold keys to our deepest questions. The satellite galaxies orbiting silently around the Milky Way are more than just astronomical curiosities. They are cosmic laboratories, time capsules, and testbeds for our most fundamental theories about the universe. In their ancient stars, their complex dynamics, and their dark matter halos, they preserve evidence of processes that have shaped our cosmos since its earliest moments. They remind us that even in the darkness between the bright stars, profound mysteries and extraordinary insights await our discovery. What happens when galaxies meet? In the vast cosmic ocean, even these island universes are not immune to the pull of gravity. When a small galaxy orbits too close to a larger one, the story often ends not with peaceful coexistence, but with a slow, graceful destruction. This process, the gradual dismantling of satellite galaxies by the gravitational forces of their larger companions, reveals one of the most fundamental aspects of galactic evolution. The process begins with tidal forces, the same phenomenon that causes ocean tides on Earth. Just as the Moon's gravity pulls more strongly on the near side of Earth than the far side, creating bulges in our oceans, the Milky Way's gravity pulls more strongly on the near side of a satellite galaxy than on its far side. This differential force stretches the smaller galaxy, distorting its shape and loosening its gravitational grip on its outermost stars. For a satellite galaxy in a stable, distant orbit, these tidal forces might remain manageable. But most satellites don't maintain safe distances. Their orbits bring them periodically closer to the Milky Way, where tidal forces strengthen dramatically. Each close passage strips away more stars, gradually eroding the satellite galaxy from the outside in. The stars lost from the satellite don't disappear. They continue orbiting the Milky Way along roughly the same path as their parent galaxy, forming what astronomers call tidal streams. These streams extend along the satellite's orbit, eventually wrapping around the entire Milky Way like cosmic rivers of stars. Over multiple orbits, these streams grow longer and more diffuse as the stars spread out along the orbital path. Perhaps the most dramatic example of this process involves the Sagittarius dwarf spheroidal galaxy, discovered in 1994. This small galaxy is currently passing through the disk of the Milky Way, less than 50,000 light-years from the galactic center. It has made several such passages in its history, each time losing more stars to tidal stripping. The result is the spectacular Sagittarius stream, a vast structure of stars that completely encircles the Milky Way at least once. When astronomers map the positions of stars in this stream, they can reconstruct the orbital history of the Sagittarius dwarf. The stream shows that this small galaxy has been orbiting the Milky Way for at least several billion years, gradually surrendering its stars with each passage. Computer simulations suggest that the Sagittarius dwarf has lost approximately 50% of its original stars to the Milky Way, and will likely lose most of its remaining stars in the next billion years. What makes the Sagittarius stream particularly fascinating is its influence on the Milky Way itself. As this river of stars moves through our galaxy's disk, its gravitational influence creates ripples and perturbations. Some astronomers believe that mysterious structures in the Milky Way's disk, such as the Gould Belt and the Radcliffe Wave, may be responses to past passages of the Sagittarius dwarf through the galactic disk. The Sagittarius dwarf is not alone in experiencing this gradual dismantling. Many of the Milky Way's satellite galaxies show evidence of tidal disruption. The Bootes 1 ultra-faint dwarf galaxy appears elongated, its stars being gradually pulled into a stream. The Canis Major dwarf galaxy is so thoroughly disrupted that astronomers debate whether it still exists as a coherent structure or has already been completely torn apart, leaving only a stream known as the Monoceros ring. Even the large and small Magellanic Clouds, despite their substantial size, are not immune to tidal forces. The Magellanic Stream, a vast trail of gas extending from these galaxies, represents material being stripped away by interactions with the Milky Way's gravitational field and its gaseous halo. Computer simulations suggest that in the distant future, both Magellanic Clouds may be completely disrupted, their stars and gas becoming part of the Milky Way. This process of tidal disruption and absorption has been dubbed galactic cannibalism, a vivid if somewhat macabre term for the way larger galaxies consume smaller ones. It represents a fundamental aspect of how galaxies grow and evolve. The Milky Way's halo, the extended region of stars surrounding the visible disk, is thought to consist largely of stars acquired from disrupted satellite galaxies over billions of years of cosmic history. When astronomers analyze the chemical composition and motion of stars in the Milky Way's halo, they find evidence of this cannibalistic history. Stars tend to cluster in chemical and dynamical space, forming what astronomers call substructures. Each substructure likely represents the remnant of a satellite galaxy that was absorbed by the Milky Way in the distant past. By identifying and characterizing these substructures, astronomers can reconstruct the Milky Way's history of galactic mergers. One particularly intriguing example is the Gaia Enceladus structure, also known as the Gaia sausage. Discovered in data from the European Space Agency's Gaia mission, this structure consists of stars with similar chemical compositions moving on highly radial orbits through the Milky Way's halo. These stars appear to be the remains of a relatively massive galaxy that merged with the Milky Way approximately 8 to 10 billion years ago, in what may have been our galaxy's last major merger event. The process of galactic cannibalism is not unique to the Milky Way. When astronomers observe other large galaxies, they frequently find evidence of ongoing mergers and tidal disruption of satellite galaxies. The Andromeda Galaxy, our largest neighbor in the local group, shows even more dramatic signs of recent mergers, with multiple shells and streams of stars in its halo, attesting to a tumultuous history of galactic consumption. Indeed, the hierarchical model of galaxy formation, supported by both theoretical models and observational evidence, suggests that all large galaxies grow in part by absorbing smaller ones. The satellite galaxies we observe today are simply the survivors, the ones that have not yet been completely disrupted and absorbed. They represent the ongoing process of galactic growth through accretion. This perspective changes how we view the relationship between the Milky Way and its satellites. Rather than seeing them as permanent companions, we might more accurately view them as future meals, cosmic snacks waiting to be consumed by our hungry galaxy. This sounds callous, but it represents the reality of gravitational dynamics on cosmic scales. In the long dance of galaxies, few small partners survive indefinitely. Yet there is beauty in this seemingly destructive process. As satellite galaxies are disrupted, their stars form elegant streams that trace graceful arcs through space. These streams persist for billions of years, marking the paths of their parent galaxies long after those galaxies have ceased to exist as coherent structures. They are like cosmic gravestones, memorializing galaxies that once were. Moreover, the stars themselves continue to shine, now as part of a larger cosmic structure. They carry with them the chemical signatures of their origin galaxies, preserving information about these lost systems. In a very real sense, the disrupted galaxies live on through their stars, their histories now woven into the complex tapestry of the Milky Way's stellar populations. The process of tidal disruption also reveals much about the structure of the Milky Way itself. The precise shapes and orientations of stellar streams are exquisitely sensitive to the distribution of mass within our galaxy, particularly the shape of its dark matter halo. By carefully mapping these streams and modeling their evolution, astronomers can measure the mass, shape, and extent of the invisible dark matter that dominates our galaxy's gravitation. Recent studies using stellar streams have revealed that the Milky Way's dark matter halo may be slightly flattened, deviating from a perfect sphere. They have also provided some of our best measurements of the total mass of the Milky Way, suggesting our galaxy may be more massive than previously thought. These results have important implications for understanding the Milky Way's place in the cosmic hierarchy and its future evolution. Looking toward the cosmic future, the process of galactic cannibalism will continue, Many of the Milky Way's current satellites will eventually be completely disrupted, their stars becoming indistinguishable parts of our galaxy's halo. New satellites may be captured, beginning their own slow journey toward disruption. And on the largest scale, the Milky Way itself may merge with the Andromeda Galaxy in approximately 4 billion years, creating a new, larger elliptical galaxy that some astronomers have dubbed Milkomeda. This future merger with Andromeda represents galactic cannibalism on a grand scale, with two spiral galaxies of similar mass combining to form a single, larger system. The satellite galaxies of both the Milky Way and Andromeda will be caught up in this cosmic collision, their fates determined by the complex gravitational dynamics of the merging process. Some may be ejected into intergalactic space, while others may be disrupted more quickly by the intensified tidal forces. As you contemplate these vast cosmic processes occurring overhead, remember that the night sky you see is merely a snapshot of an ongoing drama. The satellite galaxies visible tonight have existed for billions of years, but many will not survive for billions more. They are transient structures in cosmic terms, their stars destined to become part of the Milky Way's halo, or perhaps of a future merged galaxy. Yet in their gradual dissolution, these galaxies create some of the most beautiful structures in our cosmic neighborhood. The stellar streams that mark their disruption trace the invisible gravitational field of the Milky Way, revealing the unseen forces that shape our galaxy. They remind us that even in apparent destruction, the cosmos creates patterns of extraordinary elegance. The slow consumption of satellite galaxies by the Milky Way connects us to the largest scales of cosmic evolution. It is part of the hierarchical growth of structure that has characterized our universe since its earliest moments. From the first tiny fluctuations in the cosmic microwave background to the vast superclusters of galaxies observed today, in the quiet disruption of a dwarf galaxy, we witness a small chapter in this grand cosmic narrative. What if most of our galactic neighbors remain hidden, waiting to be discovered? Despite decades of astronomical surveys and increasingly powerful telescopes, scientists believe we have only scratched the surface in our census of the Milky Way's satellite galaxies. The night sky still harbors secrets, galaxies so faint or so obscured that they have eluded detection until now. Their discovery represents one of the most exciting frontiers in our understanding of the local universe. Why do astronomers believe there are many more satellite galaxies yet to be found? The evidence comes from multiple sources. Theoretical models, based on our understanding of dark matter and galaxy formation, predict that a galaxy the size of the Milky Way should have hundreds of satellite galaxies, far more than the few dozen currently known. While the discovery of ultra-faint dwarf galaxies has partially bridged this gap, a significant discrepancy remains. More compelling is the pattern of our discoveries so far. The satellite galaxies we found are not distributed randomly around the Milky Way. They cluster in parts of the sky that have been surveyed most thoroughly with sensitive instruments. The Sloan Digital Sky Survey, which covered about 1/4 of the sky, led to the discovery of many ultra-faint dwarf galaxies within its survey area. This suggests that similar galaxies likely exist in the parts of the sky this survey didn't cover. Additionally, the distribution of known satellites shows a curious asymmetry. We've discovered far more satellite galaxies in the northern celestial hemisphere than in the southern. This doesn't reflect a fundamental asymmetry in the universe, but rather the fact that most large astronomical surveys have focused on the northern sky, where many major observatories are located. As more southern sky surveys are completed, this imbalance will likely be corrected with new discoveries. Perhaps most significant is the zone of avoidance, the region of the sky obscured by the disk of the Milky Way itself. When we look through the plane of our galaxy, countless stars, along with gas and dust, block our view of what lies beyond. This creates a substantial blind spot in our search for satellite galaxies. Those that orbit close to the galactic plane, or on the opposite side of the Milky Way's center, remain hidden from our telescopes. Consider the challenge of spotting an ultra-faint dwarf galaxy. These systems might contain only a few thousand stars spread across a volume hundreds of light years in diameter. Their surface brightness can be thousands of times fainter than the darkest part of the night sky, as seen from Earth. Finding them requires not only sensitive instruments, but sophisticated analysis techniques to distinguish their extremely subtle signal from both foreground stars and background galaxies. The difficulty increases dramatically when looking through the disk of the Milky Way. The number of foreground stars increases by factors of thousands or millions, creating a stellar fog through which the faint signature of a dwarf galaxy becomes nearly impossible to detect with current methods. Some astronomers estimate that we may be missing dozens of satellite galaxies in the zone of avoidance alone. Distance presents another challenge. The satellite galaxies we've discovered tend to be relatively close to the Milky Way, with most within about 400,000 light-years. But the Milky Way's gravitational influence extends much further, perhaps to 1,000,000 light-years or more. Satellites orbiting at these extreme distances would be extraordinarily difficult to detect because their apparent brightness diminishes with the square of their distance. Consider Antlia 2, discovered in 2018 and one of the most diffuse galaxies known. Despite being relatively large, with a diameter similar to the Large Magellanic Cloud, it had remained undetected because of its incredibly low surface brightness. Its discovery was only possible with data from the Gaia spacecraft, which measured the precise motions of stars rather than just their brightness. How many more Antlia 2s remain undiscovered? The good news is that we are on the cusp of a revolution in our ability to detect these hidden galaxies. New survey telescopes, improved analysis techniques, and novel approaches to galaxy detection promise to substantially expand our census of the Milky Way's satellites in the coming decade. The Vera Rubin Observatory, scheduled to begin operations in the mid-2020s, will conduct the legacy survey of space and time. With its 8.4-meter mirror and 3.2 gigapixel camera, this observatory will be able to detect objects up to 100 times fainter than previous surveys. Astronomers expect it to discover dozens of new satellite galaxies, particularly in the southern sky where our current census is less complete. The Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will provide unprecedented wide-field infrared observations from space. Infrared light penetrates dust more effectively than visible light, potentially allowing astronomers to detect satellite galaxies in regions of the sky where dust obscuration has previously hidden them. Its stable space-based platform will also allow for extremely sensitive measurements of very faint objects. Perhaps most exciting are new approaches that don't rely solely on detecting the light from these faint galaxies. The Gaia spacecraft, which is mapping the positions and motions of over 1 billion stars in 3 dimensions, can identify groups of stars moving together through space, potentially revealing satellite galaxies that would be too diffuse to detect through traditional imaging. This approach led to the discovery of Antlia 2 and may unveil many more similarly elusive galaxies. Another promising technique involves studying perturbations in stellar streams from already disrupted satellite galaxies. When an unseen dark matter subhalo, which may host an extremely faint or even starless satellite galaxy, passes near a stellar stream, it creates a distinctive distortion in the stream's structure. By carefully mapping known stellar streams, astronomers can potentially detect the gravitational signatures of satellite galaxies too faint to see directly. Radio telescopes offer yet another window into hidden satellites. Some dwarf galaxies retain small amounts of neutral hydrogen gas, which emits radio waves at a characteristic wavelength of 21 centimeters. This radio emission can penetrate dust and the dense stellar regions of the Milky Way, potentially revealing satellite galaxies in the zone of avoidance. Future radio surveys with facilities like the Square Kilometre Array may detect satellites that remain invisible at optical wavelengths. What might these undiscovered galaxies tell us? Each new satellite provides another data point for understanding the processes of galaxy formation and evolution. The full census, including the faintest and most distant satellites, will help resolve remaining discrepancies between theoretical predictions and observations regarding the number and distribution of satellite galaxies. Particularly intriguing are the possibilities for understanding dark matter. Different theories of dark matter make distinct predictions about the number, mass distribution, and central densities of satellite galaxies. By characterizing a larger and more complete sample of satellites, astronomers can test these predictions more rigorously, potentially narrowing down the range of viable dark matter candidates. The undiscovered satellites may also include unique or extreme examples that expand our understanding of what a galaxy can be. Prior to the discovery of ultra-faint dwarfs, astronomers wouldn't have considered that objects with only a few thousand stars could be true galaxies. What other surprises might the faintest, most diffuse, or most distant satellites hold? Perhaps galaxies with unusual star formation histories, extreme dark matter content, or distinctive stellar populations await discovery. Some may be in the process of transitioning from galaxy to stellar stream, caught in the act of tidal disruption. Others might be on their first infall toward the Milky Way, relatively unchanged since the early universe. Each represents a different chapter in the story of galaxy evolution, a different data point in our understanding of cosmic history. There may even be satellites of satellites, smaller galaxies, orbiting the larger satellites of the Milky Way. Recent observations suggest that the Large Magellanic Cloud may have brought several smaller galaxies with it when it was captured by the Milky Way. This hierarchical structure of galaxies within galaxies reflects the nested nature of structure formation in the universe. As we continue to map the Milky Way's surroundings with increasing precision, we are likely to find that our galaxy is at the center of a far richer and more complex system of satellites than previously imagined. The few dozen known satellite galaxies may represent just the tip of a cosmic iceberg, with hundreds more waiting to be discovered. This realization reminds us of a recurring theme in the history of astronomy. The universe is often more complex, more structured, and more populous than we initially perceive. Just as early astronomers could see only the brightest stars, we now see only the brightest satellite galaxies. Just as the invention of the telescope revealed countless faint stars invisible to the naked eye, new observational techniques and technologies are revealing the faint galaxies that have remained hidden. What does this mean for our understanding of the Milky Way and its place in the cosmos? Our galaxy is not an isolated island universe, but the center of a rich system of satellite galaxies, stellar streams, and other structures, all embedded within an extensive halo of dark matter. This system continues to evolve through the processes of tidal disruption and galactic cannibalism we explored earlier. The full census of satellite galaxies, including those we haven't found yet, will provide a more complete picture of this complex system. It will help us understand how the Milky Way has grown over cosmic time, how it continues to grow by absorbing smaller galaxies, and how its gravitational influence shapes the local universe. As you gaze at the night sky, remember that between the stars you can see lie not just the satellite galaxies we've discovered, but many more still waiting to be found. These hidden companions remind us that the universe continues to hold mysteries, that our knowledge remains incomplete, and that even in our cosmic backyard, significant discoveries await. The story of the Milky Way's satellite galaxies is still being written, with many chapters yet to be revealed by future observations. Each new discovery adds to our understanding, not just of these small galaxies themselves, but of the fundamental processes that have shaped our universe since its earliest moment. In the search for these elusive cosmic companions, we continue the grand human tradition of exploring the unknown and expanding the boundaries of our knowledge. As our journey through the forgotten galaxies of the Milky Way comes to an end, let us take a moment to reflect on what we've discovered. In the stillness of night, as stars shine overhead, entire galaxies circle our cosmic home. Some bright enough to see with the naked eye, others so faint they eluded discovery until the 21st century. Together, They tell a story that spans almost the entire history of our universe. These satellite galaxies are more than just astronomical curiosities. They are time capsules from the early cosmos, preserving conditions that have long since changed in larger galaxies. They're ancient stars formed when the universe was young, their chemical compositions reflecting the simplicity of that earlier era. By studying them, we glimpse the universe as it once was, before billions of years of stellar evolution enriched the cosmic environment with heavier elements. They are laboratories for understanding dark matter, that mysterious substance that makes up most of the mass in our universe but cannot be directly observed. In the ultra-faint dwarf galaxies, dark matter dominates overwhelmingly, making them ideal environments for testing theories about its nature. The number, distribution, and internal structure of these satellites provide crucial constraints on how dark matter behaves and how it shapes the formation of cosmic structures. These forgotten galaxies also reveal the processes by which larger galaxies grow. Many are being slowly torn apart by the Milky Way's gravitational forces, their stars forming streams that wrap around our galaxy. Over billions of years, these stars become incorporated into the Milky Way's halo, contributing to its growth and complexity. The satellite galaxies we observe today are the survivors, the ones that have not yet been completely disrupted and absorbed. Yet even in their gradual dissolution, these galaxies create structures of extraordinary beauty. The stellar streams that mark their disruption trace graceful arcs through space, revealing the invisible gravitational field of the Milky Way. They are like cosmic rivers, flowing through the darkness between stars, their currents carrying the remnants of once independent galaxies, and we have only just begun to find them. Despite decades of searching, astronomers believe we have discovered only a fraction of the satellite galaxies orbiting the Milky Way. Many more likely remain hidden, too faint to detect with current instruments or obscured by the disk of our own galaxy. Each new survey reveals more of these elusive companions, gradually completing our census of the local universe. Time and gravity have made companions of these galaxies. Some may have formed alongside the Milky Way, emerging from the same vast cloud of gas in the early universe. Others may have been captured later, their independent journeys through space interrupted when they strayed too close to our galaxy's gravitational pull. Now they orbit silently, their futures intertwined with that of the Milky Way. As you drift towards sleep, imagine these forgotten galaxies continuing their orbits overhead. The large and small Magellanic Clouds slowly track across southern skies. The Sagittarius dwarf galaxy passes through the disk of the Milky Way, leaving a stream of stars in its wake. Dozens of ultra-faint dwarf galaxies move almost imperceptibly against the background of more distant stars, their light too faint for human eyes to perceive. Some will eventually merge with the Milky Way, their stars becoming indistinguishable parts of our galaxy. Others will continue their orbits for billions of years to come, silent witnesses to the ongoing evolution of our cosmic neighborhood. All carry within them the memory of the early universe, preserved in the chemistry and motion of their stars. These forgotten galaxies remind us of our place in the cosmic hierarchy. The Earth orbits the Sun orbits the center of the Milky Way, and the Milky Way itself is surrounded by an entourage of smaller galaxies, all moving together through the vastness of space. And our entire local group of galaxies moves relative to other galaxy groups and clusters, part of the great cosmic web that spans the observable universe. They remind us too of the extraordinary reaching of human knowledge. Through careful observation and analysis, through the development of ever more sensitive instruments and sophisticated theories, we have discovered these faint companions and begun to understand their significance. From our tiny planet, we have mapped a system of galaxies spanning millions of light years, piecing together their histories and relationship. Yet for all our knowledge, much remains unknown. The full census of satellite galaxies, their complete histories of formation and evolution, the exact nature of the dark matter that dominates them, these questions await future discoveries. The night sky still holds secrets, galaxies yet to be found, processes yet to be fully understood. Around the Milky Way, the forgotten galaxies still turn. They do not shine bright, they do not call attention to themselves, but they remain. Sleep now, knowing that the sky remembers even the faintest things, and it holds them close.